work and energy. So make sure you put that today's date up at the top of your notes so that you can keep track of when we learned what. Work. All right. Work is a scalar quantity, and it is a result of a force that causes a displacement. It is also the process by which energy is transferred through a force. Both of those definitions would appear in the vocabulary section of a test if I were to do that, okay? So either of those would be appropriate answers. If I asked you to define work, then I need both of them from you because they're both valid. That it is the result of force causing displacement on an object, and it's a process by which energy is transferred through a force. All right, so we've got a formula there. This is a boxed equation, so this must mean it's on your formula chart. Work is equal to force times displacement times the cosine of theta. Does that look somewhat familiar to you? What does it look like? Yeah, it looks like torque, right? So we know that the formula for torque was force times lever arm times sine theta, right? And we had said that torque was a vector quantity, correct? All right. And because it was a vector, it had magnitude and direction, and we kept the units as Newton meters, right? But work is a scalar, okay? So we're going to change the units. If I got the units out of this formula, it would be the units of force, which is newtons, times the unit of displacement, which is meters, and I would also get Newton meters. You can't have two things with the units of Newton meters if they're different things, right? So this whole term right here, Newton meter, changes into a new unit called joules. Okay. All right, so let's go through what each of these variables stands for in our work equation. F, of course, is the force that is doing the work. That's very important because there are situations in which you'll have multiple forces acting on an object, but it is about your perspective, okay, or the perspective of the question. Which force is the one that's actually doing the work? That's the one that you got to pay attention to, and I'll give you an example of that in just a minute. Letter D is obviously for displacement. Of course, that's going to be how far the object moves in meters. And then theta is going to be the angle between the force vector and the displacement vector. We're separating it based on which one's a vector and which one's a scalar. So we change energy or work into joules, and we kept torque as Newton meters because that one's a vector. That's really it. All right, everybody have all that stuff written down? So when using this formula or that equation, you're going to use only the magnitude of the force and the displacement, all right? So if it was like a negative force or a negative displacement, we don't care. Do not put the negative sign in there. You do the magnitude only, okay? If you end up putting the sign in there, you're going to flip things. You're going to make it wrong, all right? The cosine of theta, the reason that term is there is to provide the sign for you. So if you put the sign in, you've actually flipped it opposite of what it really is, okay? All right, so let's talk about the differences between work in terms of how we define it with physics and work and how we define it with your everyday life. Okay. So somebody, or multiple people, but just raise your hand and tell me something when you hear the word work, what do you think of? Okay, Garrett. Okay, mowing a lawn. A desk job, all right. What else? Okay, exerting energy. If you're working, you're exerting energy. What else? I don't know what that means. Putting out the new mixtape, okay. All right. What else is work? If you were to see someone working, what would they look like? Sweating. Okay. So those are all of our ideas of what it means to work, or or if somebody else is doing work, that they have to be sweating and all this stuff, right? Okay. Now physics says that all you are doing is causing something to move by applying a force to it, right? Um, so let's see here. Who wants to be my guinea pig? Okay. All right. Well, I'm going to pick Brady because he's closer. All right. Brady, hold your hand out like this, please. Okay. No, palm up. You're going to want to put the pin down. There you go. Okay. All right. Now, please keep them right there, Brady. All right. Keep them right there. No, please don't move them. No, put them back out. Come on. Brady, if you could just.
I'm like shaking like a dang. It's harder than you thought. You shake so bad.
All right. So cool. No,
it's so hard to do without shaking.
Please don't move it. Just keep it right there. Same. Okay. Now, Garrett, up. Right here. Right there.
Okay. Don't chew with that. Don't chew with that. Don't chew with that.
All right. Garrett, are you working?
I'm working. I'm about to say you're not working.
You're not working. It's not moving.
There's no work happening right now. Okay. Is he applying a force? Yes, he is. Which way is his force pointing? Up. Are these books moving? They're not. They're not supposed to, right? So that means he's doing no work. Do you feel like you're working?
Yeah, I'm getting a good old left arm.
Okay. Why? Why do you? Physics says there was no work happened. Zero work happened. Okay. Yeah. The work that was occurring, according to physics, is actually happening inside his muscles. Okay. There was a force that was causing his muscle fibers to move back and forth. Okay. Every time his nerves told his muscles to contract, the muscle fibers pulled in. That was a force causing a movement, right? All the work happened inside the muscle. No work was done on these books. Work was done on the muscles, okay? You understand the point that I'm making? You have to figure out which force is actually doing the work, okay? His force on the books wasn't doing any work. The force that caused his muscle fibers to contract, that was doing the work there, okay? So that's one case, all right? Let's see. Let's see if you can answer this question, all right? So am I applying a force? Yes, okay. Now watch what happens and you tell me if I'm doing any work, okay? I'm applying a force. Is the object moving?
Yes.
Okay.
Yes,
the object is moving. Now answer this question. Did I do any work on the book?
No.
Somebody raise your hand and tell me why. Josh?
Because the force you were applying to the book wasn't what was causing it to move.
Okay. What was then?
You moved it. Like your body, you walk it.
Well, how's the book going with me?
It's friction.
Okay. Which way is the friction force acting?
The opposite of whichever way you're walking.
Okay. So it wasn't my upward force that was doing anything with this book, right? Let's see if we can use the formula to explain a little bit more detail, okay? We'll use the definition of theta. What was the definition of theta in the work formula? Okay, the angle between the force and the displacement, right? So let's say I've got my upward force, so the force vector is this way. The displacement vector was that way. What's the angle between that and that? 90 degrees. What is the cosine of 90 degrees? 0. What's 0 times force times displacement? 0. So there was no work done on the book, right? Does that make sense? Exactly. Now let's do it again, okay? Am I applying a force on the book? Okay. Now, I displaced the book now, right? Okay. So my force vector points in which direction? Up. My displacement vector points in which direction? Up. What's the angle between up and up? 0. Okay. So what's the cosine of 0? 1. All right. So did I work on the book? Yes, I did. I did do work. Now the question is, what kind of work? Did I do positive work or did I do negative work on the book?
There is none. It's the magnitude.
All right. So Shivam says there is no such thing as positive or negative work because it's scalar, right? Well, now let's see here. let's talk about something else that's scalar. Let's talk about money, right? Money's scalar. I don't owe you $5 to the east, right? Okay, so money is scalar. Can you have positive money?
Yes.
Can you have negative money?
Yes.
Yeah, it's called debt. All right. So can you have a negative scalar quantity? Yes, you can. Okay. So what kind of work did I do on the book just now? Positive. Now let's play the game again. All right. Watch the scenario. Okay. Now point in the direction of my force. My force vector is still this way the whole time. Okay. What was the direction of my displacement? Down. What's the angle between up and down? 180. What's the cosine of 180?
-1.
-1. So what kind of work did I do when I did this? I did negative work on the book. Okay? Yeah. Yes, it is. Oh, no, there is. Because we said I was the one applying the force, right? Let's think about it from a different perspective. Mine is not the only force acting on this book. Yeah, gravity's the other force, right? Way to go, Brady. All right, so now let's look at it from gravity's perspective, okay? Same two situations, all right? I'm going to push up on this, but I don't care about my force. I care about gravity. Which way is gravity pointing? Down. Which way is the displacement vector pointing? Up. What's the angle between up and down? 180. What's the cosine of 180? So what kind of work did gravity do on the book? Negative. All right, now let's do it. Okay, which way is gravity pointing? Which way is the displacement pointing? What's the angle? 0. What's the cosine of 0? So what kind of work did gravity do? Positive work, all right? So when I do positive work, gravity's doing negative work. When I do negative work, gravity's doing positive work, right?
So basically, if the displacement, like if the force is acting in a different direction of the displacement, then it's going to be negative.
Now, let's talk about why that is, okay? What I just did, and according to the definition of work, is it is a transfer of energy through a force, right? I had to use up energy in order to apply that force to the book, correct? And when I did that, I made the book move. Anybody know what kind of energy we call it when something moves? No. What is the energy of motion? Say it. Kinetic energy, okay? Because I made the book move, I gave it kinetic energy, correct? I also raised its position above the surface of the earth. Anybody know what that kind of energy is called? Gravitational potential energy, right? Okay, so we have two different kinds of energy going on here. Now, energy can't be created or destroyed, right? It can only be transferred. So what I'm doing is I am taking energy from the earth and I'm transferring it into the book, all right? By raising its position above the surface of the earth, I'm giving this the potential to move later on, right? If my hand were to vanish out from underneath this book, what would happen? The book would return to earth, right? So it's like a bank account, okay? So when I put the book down here, it has no potential to move, right? Zero energy there, okay? When I raise the book, okay, I am doing positive work on the book. I am taking energy from the earth. So gravity is doing negative work. Does that make sense? Okay, if I let go or I let the book move downward, then I'm giving energy back to the earth. The book is returning and it's losing all that potential energy. It's converted into kinetic energy, right? Okay. There you go.
It broke.
All right. The book broke. Okay. All right. So let's go ahead and write that stuff down. Let's answer some of these questions. My first scenario there, what was the direction of my applied force? Up, okay. My force on the book was up, okay. What was the direction of displacement? Up, okay. And so what did we say that angle was? 0 degrees. And what was the cosine of 0? Okay, so what kind of work was done? Positive work. Okay. What's up? All right. Yeah, as it passes by other planets, gravity could be pulling on it, slowing it down. It could run into tiny micro particles that are bombarding it and taking energy from it. All that kind of good stuff. All right, now let's do this next set here. What if the book was lowered? Which way is the force going to be applied? Still up. Which way is the displacement vector? Down. What's the angle there? 180. What's the cosine of 180? What kind of work is done? Negative work. Because these two vectors are both pointing in the same direction, so there's no angle between them. But when I flip it, then it's 180 degrees apart. All right. So now let's see. Let's answer this question. What about from the perspective of the force of gravity? So in the first scenario, what kind of work did gravity do? Negative work. And then in the second scenario, what kind of work did it do? Positive work. It's up to you. If you'll remember my demo, then no, you don't have to. If not, then you may want to. All right, it says always identify the force that is doing the work. Okay, that's very important. So let's talk about units. Okay, so I've already done these units here. Force was newtons, displacement's meters. We changed that from newton meters into joules for this scalar thing. Okay. I also already talked about this scenario here that we can have a negative scalar quantity. And now let's do a practice question, because we love practice questions. All right, a shopper pushes a cart with a force of 35 newtons at an angle of 25 degrees. Of course, we're going to assume that's with the horizontal. Find the work done by the shopper as, I should say they, okay, as they move along a 50-meter path. Okay, so the person's pushing that cart, right? Their force vector, remember the way that we draw a free body diagram, the free body diagram always shows the arrow moving away from the origin, right? So what I'm going to do is I'm going to move this force vector here through so that it comes down from the other side, right? Okay, so I've got my force vector, my applied force here, and it's going to be 25 degrees with the horizontal. Everybody all right with that? Let's go ahead and see. It wants to know the work done by the shopper. So the force that we're talking about here is what? What force? The applied force by the shopper, right? Okay, so I'm going to say work is equal to force times displacement times the cosine of theta. So that's going to be my 35 newtons times, what is the displacement of the shopping cart? 50 meters times the cosine of, now, by definition, theta is the angle between the force doing the work and the displacement, right? So my displacement vector is this way, okay? My force vector is that way. What's the angle? 25, okay? No, that's a 25. Okay, how many sig figs should you tell me? No. 2. All right, so what is it? All right, 1,600 joules. Raise your hand if you agree with that. Okay. Very good. Okay. Yeah, just J. Okay. 1,600 joules. Now you'll have it. All right. How much time do I have left? Sweet. Okay. So any questions about this? That should be fairly easy, right? Plug and chug kind of formula. All right. Next. Okay. So now we're going to talk about energy. All right. And work and energy kind of play in the same field there. Okay. Remember, work is transferring energy to an object through a force, right? So they are tied to each other through forces. Now let's talk about all the different kinds of energy. The first one we're going to talk about, we've already mentioned in this class period. We said it's kinetic energy. And this is the energy of motion, and it is a scalar term as well. In fact, all energies are scalar. We have a boxed equation for you for kinetic energy. kinetic energy is equal to 1/2 the mass times the velocity squared, where m is the mass of the object in the standard unit, kilograms, and v is the velocity of the object in the standard unit, meters per second. So let's look at the units then for energy, okay? We know that energy, that's going to be mass, right? So there's your kilograms. And then we've got velocity squared. And the unit for velocity is meters per second, right? And if you square that, you have to square both pieces. So you have meters squared over seconds squared. That's where this comes from right here. Everybody cool with that much? Now I'm going to factor an m out. Okay, so I've got kilograms times meters per second squared times meters. Well, kilograms, that's mass, and meters per second squared, what's that the unit for? Acceleration, right? What is the unit that you get when you have mass times acceleration? Newtons, okay? Because that's the formula for force, right? Force equals mass times acceleration, and the unit that you would get from that is newtons, correct? So when I say kilograms times meters per second squared, that's the same thing as saying newtons, okay? So then that means I can change this into newton times meters, and we know that that then becomes joules, okay? So that's how come the unit for kinetic energy is still joules, even though it looks completely different than the formula for work. Okay, now here's a question. Can you have negative kinetic energy? Why or why not? Think about that for a moment, please, before you answer. Can you have negative kinetic energy? Why or why not? Brady? Brady says yes. Tell me why you think that. Okay, Brady says that just because this is a scalar quantity is no reason for it not to be able to be negative, right? But let's delve deeper. Isaac? We set up our axis to say that things that move to the left is negative, and down is negative, and backwards is negative. Yeah, we could have a negative scalar, so there's a different reason. Garrett? I'll give you a hint. Listen, there's something about the formula that clues you in. Okay, something about the formula. All right, Siobhan? There's no cosine or sine of theta. Graham? Very good. Okay, because velocity is, I could have a negative velocity. That's possible, right? You can't have a negative mass, but you could have a negative velocity. But when you square it, that negative sign goes away. There is no situation that I could plug into that formula and get a negative answer out of it. Okay, so you cannot have negative energy because velocity is squared. So write that in there. No, because we just went through the units here, and it has to be squared in order for the units to create joules, right? So like this must be the equation for kinetic energy. We didn't just say, I think we'll square it this time. Like you have to do it so that you get the right unit there. Let's look at the next kind of energy. We have potential energy, which is symbolized with a capital PE. Of course, kinetic energy was capital K, capital E. And there are going to be multiple kinds of potential energies, all right? The first kind that we're going to talk about is gravitational potential energy. So the way that we signify this, we make it different than the other potential energies we're going to discuss, is we have to put our little g as a subscript, all right? So capital P, capital E, little g. And that's going to be our gravitational potential energy. It too is a scalar quantity. We have a boxed equation for you here that will be given on any quiz or test. Gravitational potential energy equals to mass times little g times h, where m, of course, is the mass in kilograms. Little g is the acceleration due to gravity using the magnitude only, so it's going to be positive. We'll never put it as a negative. And then h is going to be the vertical height above what we call a zero line. And we'll define that in just a moment. The vertical height above a zero line. Okay, let's look here, zero line, okay? A zero line is a horizontal line that is the reference point that you set for the problem. You get to pick wherever you want your zero line to be. Several things. There are 3 things that you must do on any energy problem, and I want you to star this second bullet here. box it, put it in the cloud, highlight it, something about it. You need to know those three things. Any energy problem, you must do these things. Actually, any energy or work problem. Okay? You must always select an initial point, a final point, and a zero line. Without those three things, you cannot work an energy or work problem. Just like without the axis of rotation, you can't work a torque problem. Right? Okay, so here we are looking at the units of mgh. Mass, of course, is kilograms. G, acceleration due to gravity, meters per second squared. And h is a distance or a height, that's meters. So again, we're going to get our kilograms meters squared per second squared, which is newtons times meters, which is newton meters, which is joules. Good question. Can you have a negative gravitational potential energy? Yeah, you can. There is no reason you can't from that formula. All right. So zero line, we talked about that yesterday. That's the horizontal line. It's a reference point that you set for yourself. And then, of course, you always have to select initial position, final position, and a zero line for any work or energy problem that you do. And then I gave you the units here. How do we get from the units for energy all the way back to joules here? And this is m, this is g, the acceleration to gravity, and this is h, some height, which is measured in meters, and we get to joules, okay? So let's talk about that zero line real quick, okay? How fortuitous that I have an empty seat up front, okay? All right, so let's say that I set the floor as my zero line, okay? Do I have gravitational potential energy? Yes, because I am at some vertical height above the zero line, right? Okay, let's say that I set the zero line where the desk is, okay, like where my feet are standing. Do I have gravitational potential energy? No, because I have zero vertical height above the zero line. This is our frame of reference. It's your perspective. It's how you're working the problem. Mathematically, if you want all of your numbers to come out right, you have to be consistent. Wherever you said the zero line was, and wherever you said the initial position and the final position are, you stay consistent with it throughout, and all of your numbers, your answer, your math is going to come out correct, okay? But we know you really aren't going to have a negative gravitational potential energy, because the whole idea of gravitational potential energy is how far you are above the surface of the earth. Does that make sense? So even when I was standing up here and I said my zero line is the desk, okay, we really know that I am above the surface of the earth, right? So did I actually really have gravitational potential energy when I was standing on this desk? Yeah, I had the potential to move. I could have fallen off the desk, right? All right, when I stepped down, I moved. I converted the gravitational potential energy into kinetic energy. Does that make sense? Okay, so just understand the way that you look at the problem will affect how you do your math, but ultimately you can't have negative gravitational potential energy. So let's do the next kind of potential energy. Remember, I told you there were several kinds of potential energy, and we designate them by putting a subscript after the PE, okay? So here we're going to have elastic potential energy. So that's going to be capital P, capital E, and that is supposed to be a lowercase e after that. My Word document changed it, okay? So capital P, E, lowercase e. So that's elastic potential energy, okay? It is a scalar quantity, just like all energy and work. And it, of course, is, by definition, the energy stored in an elastic material. So, we're thinking springs and rubber bands traditionally, all right? Obviously, there's other things out there that have elastic quality to them, but for pretty much all of our practice questions that we're going to do, we're going to be talking about springs or rubber bands, and usually it's going to be predominantly springs. Okay, so here is your boxed equation for elastic potential energy. hopefully you notice that there's a similarity between this and what other energy formula? Kinetic energy, okay? What was the equation for kinetic energy? Very good, 1/2 mv squared, and this one is 1/2 kx squared, okay? So let me ask you the same question as I did for the kinetic energy. Is it possible to have negative elastic potential energy? Why or why not?
No, because that's
Very good. No, because the x term is squared, and that would get rid of our negatives, okay? Now, let's talk about what each of those variables are there. K is known as the spring constant, okay? And that's different for every spring. It's like a fingerprint, okay? And what that is a measure of how difficult it is to expand or compress a spring. If you have a very large spring constant, then it must be very difficult to compress or expand a spring. And if it's very low, then it would be very easy. So, with that in mind, do you think that a slinky has a high or low spring constant? Very low. Do you think that the shock absorbers on a monster truck have a high or low spring constant? Very high, okay? So keep that in mind. Now, our dimensions on spring constant are newtons per meter, okay? Please don't get that confused with the units for torque or for work, the Newton meters. This is newtons per meter. So let's look at our displacement here. This x is the displacement from the equilibrium position, okay? So the equilibrium position is going to be the 0 line, okay? Now, there are a couple of different situations for a spring, all right? A spring could have multiple equilibrium positions, and again, this is based off of how you look at it, okay? So if I have, just a spring laying on my desk here, okay? And nothing is compressing it, nothing is stretching it, then the spring is in equilibrium, correct? So this is its equilibrium position, okay? That's the 0 point, all right? If, for example, though, I change my scenario and I have, say I have a spring that is attached to, some immovable object up here, ring stand or whatever, and I hang a hanging mass from that spring. That's going to stretch the spring down from what it normally would have been, right? Okay, normally, let's say my spring maybe stopped right there when there was no mass on it. Does that make sense to everybody? This point right here would have been the equilibrium position. Or, that's one way to look at it, where I knew where it was beforehand. Or I could say that right here is the equilibrium position because I intend to stretch this spring even further, right? If I hang a mass from a spring and I let it stop so that it's not bouncing up and down anymore, this could be what we call our new equilibrium position. And now I'm going to stretch that mass down and let go, and then the spring is going to bob back and forth, up and down. Does that make sense? So in that case, if I'm looking at it from that perspective, then down here is the equilibrium position. Does that make sense to everybody? Okay, so you have to know, what you're going to be doing in that problem in order to decide where your equilibrium position is going to be. All right, let's go back here. Do we have all the rest of this stuff written down? Not yet? Okay. So then, of course, example, I already did that, slinky and shock absorbers. Okay, so let's talk about units, okay? We're, of course, again, going to use our equation, the k times x squared, the 1/2. Does that have any units? No, so I don't care about that. All right, what's the unit for k? And what's the unit for it? Very good, newtons per meter. Of course, I have this written out right here, okay? And now x, that's a displacement. What do we measure displacement in? Meters, of course, that's squared. So one of these meters cancels one of those meters, which gives us what? Newton meters, and we change that into joules, okay? Yep, Any kind of energy is joules. All right. And then, of course, Brady's already answered this question right here for us. Can we have negative elastic potential energy? Why or why not? And what do we say? No, because x is squared. That has a squared term in it. All right, so let's do a practice question then, okay? The staples inside a stapler are kept in place by a spring with a relaxed length of 0.115 meters. If the spring constant is 51.0 newtons per meter, how much elastic potential energy is stored in the spring when its length is 0.150 meters? Okay? All right, so we have a relaxed length of the spring, right? So let's say here's our relaxed length. And this is going to be our equilibrium position. Right there. That's our equilibrium position. Ekpos. Okay? Now, did the spring get expanded or did it get compressed in this problem? It had a relaxed length of 0.115, and then it changed to 0.150. So what do we say? It expanded, right? Okay. So our new example, and this is how I do all of my elastic potential energy questions. I draw the original scenario first, then I draw what the new scenario is going to be. Okay? And you carry your equilibrium position down through both pictures. Okay. Put what where? Because it was the end of where my spring was. Okay. So we know then that this distance right here, from the movable wall or whatever the spring is attached to inside the stapler, out to the equilibrium position is going to be 0.115 meters. And we know that the distance out to its new stopping point out here is going to be the 0.150 meters. And we know that we have a K value equal to 51.0 newtons per meter, right? And we have been asked to calculate what is the elastic potential energy of the spring, or stored in the spring in this case. So what's the formula for elastic potential energy? Okay, cool. So we're going to say equals 1/2 times, what's K? Naked number. Very good. Newtons per meter. Times, now X is what? What is, by definition, what is X? Yeah, that's the displacement from the zero line, okay? How are we going to find that?
0.150 minus 0.115.
Good. We know that this right here is X, okay? We need to subtract to figure out what that little piece is right there. All right. What's the unit on that, Mark? Perfect. And then we need to do one last thing to this. Square. Okay. All right, so type all that good stuff in your calculator, please. Okay, raise your hand if you agree with Mark. 0.03 joules.
Wait, that's not 2 sig figs.
Sorry, Mark. So close. That is not 2 sig figs. That's only 1 sig fig. All right, Brady.
0.031.
Okay. Raise your hand if you agree with Brady. All right. No, right here, that's just 2 sig figs.
Yeah, that's yeah, that's 3. It's not?
No.
I thought it was after. If it was after a whole number, then it was.
No, the rules for sig figs say that if you have a number that's got a decimal in it, you start on the left, right? Oh yeah, you're right. There are 3 sig figs. Crap. Okay. I hate being wrong on film, no less. What? Okay, off you go. Okay, so then what is it with 3 sig figs?
0.312.
All right, 0.312 joules. No, you did not. Oh, that. You know what? That's true, Mark. That is very true. Okay, so everybody's got this? Yeah? Awesome. Okay, let's look at this next part here, okay? There's one more type of energy, but we will get to that one towards the end of the year, okay? So we're going to deal with the 3 types that we just learned: kinetic energy, gravitational potential, and elastic potential. And all 3 of those together are what we call mechanical energy, okay? And so this next section is going to be conservation of mechanical energy. That is only true if there is no friction, okay? Conservation of mechanical energy is only true if there's no friction. Raise your hand if there's ever a situation in which there is no friction. Okay, so this is a hypothetical situation that we are basing this off of. What's the point then? Why would we possibly learn something that's not really going to ever happen? Okay, same reason we did, stoichiometry in chemistry, right? When I said, are we ever going to get 100% of the reactants out of the beaker and create 100% of the products? No. So why are we bothering to learn this? What does that give us? A reference point. Yeah, it gives us a baseline. So if we know what the situation would be like without friction, then it makes it easier for us to figure out what it's going to be like with friction. Okay? Can you make sure that gets to him? Okay. Okay, so let's start out with this small equation here. Somebody get out your formula chart and tell me if I put that on there. I don't think I did. Mechanical energy initial equals mechanical energy final. Is that on there?
It's with a not and a F, but yeah.
Okay, so that is on there, okay? Yeah, so this is a boxed equation then. I did give that to you, okay? Mechanical energy initial equals mechanical energy final. That's conservation of energy. All the beginning stuff equals all the ending stuff, right? Oh, hey, I even said it right there. Will be given. Cool. Again, for this equation to work, since it's got energy in it, you must pick an initial point, a final point, and a zero line, okay? All right, so I'll give you a chance to write that down, and then we can work that practice question. A bird is flying with a speed of 18 meters per second over water when it accidentally drops a 2.0 kilogram fish. Assuming the altitude of the bird is 5.40 meters and disregarding friction. Now, what do we mean disregarding friction? It's air resistance. Very good. What is the speed of the fish when it hits the water? Let's go ahead, and first thing we want to do here is draw ourselves a picture, okay? So, let's see. Got my water down here, and I'm not really going to worry about the fact that there was a bird because it's the fish that's going to be falling, right? So here's the scenario, right? So the bird has just dropped the fish, okay? And the bird, let's say, was moving to the right, okay? Which means that this fish has some kind of initial velocity to the right, correct? But the fish is no longer attached to the bird, which means it can't stay up in the air anymore. So gravity starts affecting the fish. You can just leave him right there. All right, so gravity starts affecting the fish, which means that the fish starts falling. So what kind of motion is the fish in now? Well, that's part of it. Yeah, it's in 2D motion, okay? What do we call two-dimensional motion? It has a special name. Starts with a P. Thank you. Projectile motion, okay? So the fish is now in projectile motion or two-dimensional motion, okay? It is moving in the X and Y axis at the same time. Let's go ahead and we're going to always, when we've got a problem like this, we're going to do three things because this is based off of energy, right? So somebody tell me one of the things we're going to do. Okay, where would you like the zero line to be? Okay, so we would like the zero line to be where the water's at. Okay, what now? What else? Somebody else tell me something. Somebody else. It's another thing we got to do. Josh? Where would you like the initial point to be? Okay, so let's make this the initial point. And what now? Isaac? Where would you like that to be? Okay. Very good. Okay, so I've done the three things I'm required to do now. Okay, now I'm going to write down my equation. Okay, what equation am I going to use? Almost.
No, wait. No. Gravitation.
No, Graham is almost right. Conservation of mechanical energy equation. Very good. Okay, so we're going to say, what is that? What is the conservation of mechanical energy? All right, very good. So mechanical energy initial equals mechanical energy final. Now, you are required, until I say otherwise, to expand both sides of the equations with all types of energy, all types of mechanical energy, okay, until I say you don't have to anymore. So, what are all the types of mechanical energy? Now, you look at the situation and we decide what kind of energy does the fish have. Okay, so when the fish is up here at this initial point, tell me all the kinds of energy that the fish has at that location. Okay, it's got kinetic because it's moving, and it has gravitational potential energy. So it does not have the elastic, so we can get rid of that one.
Now, what other kinds of energy does the fish have at the beginning of its trip? Obviously, it's going to have some initial kinetic energy because it's moving, and it's got some gravitational potential energy because it is above the zero line. Alright, so at the end of the trip, we know that the fish is not running into a spring, so there's no elastic potential energy. We know that the fish is going to be on the zero line, so there can't be any gravitational potential energy at the end of the trip. But the fish is still moving. When we say that it hits the water, we're actually meaning that it's right above the surface of the water. So it does still have some velocity, which means there is some final kinetic energy. Alright, now let's rewrite what's left over. We have kinetic energy initial plus gravitational potential energy initial, and that's equal to the kinetic energy final. Alright, now at this point we're going to use the formula for each of these types of energy to expand the equations even further. So for the kinetic energy, we've got 1/2 the mass times the initial velocity squared because we're at the initial point. Then we've got the gravitational potential energy. So that one's going to be mass times little g times the initial height. Mass times little g times the initial height, because again we're on the initial side. And that's equal to 1/2 the mass times the final velocity squared because we're on the final side now. Alright, what do we notice? Everybody brought mass to the party, so we can go through and cancel mass out in all of these terms. Alright, now let's rewrite what's left. We've got 1/2 times the initial velocity squared plus g times h naught equals 1/2 times the final velocity squared. Alright, so what do we do now? We're trying to get that final velocity alone, so we need to get rid of the 1/2 fraction there. So let's go ahead and multiply everything by 2. And when we say everything, that means every single term needs to be multiplied by 2 here. Alright, now let's take the square root of both sides of the equation, and then we'll have our final velocity is equal to, then we'll rewrite our square root. And remember, anytime you introduce a radical, you also need to make sure you put your plus or minus in front of that. However, we were asked for the speed of the fish, so we don't really care if it's plus or minus, so we can get rid of that. We only want the magnitude, not the direction this time. Alright, plug all that in your calculator, and you should get 20.7 meters per second. At this point, we've actually reached a place where we can do more than one kind of method to solve the problem. We can go back to our kinematic equations and look at v final squared equals v initial squared plus 2a times delta x and get the same answer. If you'll notice, the formula that we got by doing our energy problem above looks exactly like the formula we would get if we did our kinematic equations and solve for the final velocity, where our acceleration is little g and our delta x is the original height of the fish. A 2-meter long pendulum is released from rest when the support string is at an angle of 25 degrees with the vertical. What is the speed of the bob at the bottom of the swing? Okay, so here's our picture, and this is an energy problem, so we're going to use the conservation of energy equation. So that's going to be our ME initial equals ME final. And now we expand on both sides. So we've got kinetic energy initial plus gravitational potential energy initial plus elastic potential energy initial is equal to kinetic energy final plus gravitational potential energy final plus elastic potential energy final. Now let's cross out what's not there. We have no kinetic energy at the beginning because the initial velocity is 0. We do have gravitational potential energy because it's above the 0 line. We do not have elastic potential energy because it was not released from a spring. We have no gravitational potential energy at the end because it's on the 0 line. So there's the 0 height above the 0 line, and we have no elastic potential energy at the end because, again, it did not run into a spring or a rubber band. All right, let's expand with what we have left. So we've got mg h naught for the initial gravitational potential energy is equal to 1/2 the mass times the final velocity squared for our final kinetic energy. And that's it for all of the energy initial and final. Everybody brought mass to the party, so we can cross out the mass on both sides, and then we can rewrite what we have left. We have g times the initial height is equal to 1/2 times the final velocity squared. Now we're after that final velocity or the final speed, so let's multiply everything by 2 and take the square root of both sides. So we have the final velocity is equal to the square root of 2 times g times h naught. Alright, let's define h naught. Okay, remember that is the vertical height above the 0 line. So this is our h naught right here. And let's just draw a little horizontal line from the middle of that plumb bob over. And hopefully you're starting to see something here. We can go ahead and expand this height all the way from the top here all the way down to the 0 line. That's the length of the string. So we know that that's 2 meters long. And we can hopefully see now there's like a triangular shape here, so we can shade that triangle in a little bit more so that we can focus on this and maybe define a few parts here so we can try and figure out what that h naught value is. Alright, let's zoom in here a little bit. Okay, so I'm gonna call this this side here, I'm going to call this side Y of our triangle. And I'll tell you why I'm doing this in just a second. But I'm going to call this side Y. Now let's come up with an equation. I can say L, the length of the string, is equal to 2 meters. Okay? And L, the length of the string, is also equal to side Y plus H naught. So now I can set both of those things equal to each other. I could say that Y plus H naught must be the full length of the string, 2 meters. Does everybody see that? Now let's use some trig. We can say that the cosine of theta is equal to the adjacent over the hypotenuse. So that's going to be our cosine of theta is equal to Y over L in this case. If we rearrange to solve for y, we say that y is equal to L times the cosine of theta. Alright, now let's use this equation up here and solve for h naught. So we can say that h naught is equal to L minus y. And now we can make a substitution with the other equation we got from our trigonometry just a second ago. We'll substitute in h naught equals L minus, and then all this stuff up here is y, so we'll just substitute it in and say L times the cosine of theta. And now all of this we can go substitute back into our final velocity equation over here for h naught. So let's rewrite that, and we end up with V final equals the square root of 2 times G times the quantity of L minus L cosine theta. Alright, plug all your numbers in, and you should come up with 1.9 meters per second squared.
Now, because I didn't hear my 3, 2, 1. Yeah. So, all right. So let's look at the next thing here, okay? Did y'all write this question down yet?
No. Yes. I have.
Okay. All right. If you haven't, I will give you 1 minute. You have exactly 1 minute. A block compresses a spring 35.0 centimeters and is then released. The block travels along a level, frictionless surface until it comes to an upward slope inclined at 25 degrees with a coefficient of kinetic friction of 0.260. The spring constant is 560 newtons per meter. Find A, the maximum height up the ramp the block travels, and B, the work done by the force of gravity. I'm going to draw my picture, which is going to be quite elaborate. This picture is actually in 2 parts. We're going to split this up into 2 different sections, okay? So we have a part here at the beginning, right before the box goes up onto the ramp. This is going to be part 1 where we have 0 friction, okay? Then we have a situation where the box moves onto the ramp and there is friction along that ramp, okay? So there are 2 clearly different scenarios happening here, okay? And the first thing that we're trying to figure out, or one of the things that we're trying to figure out, is the maximum height up the ramp that the block travels, okay? And then, of course, we want to know the work done by the force of gravity on the box, all right? So let's deal with the level surface first, okay? Well, let's talk about that work done by the force of gravity then for a second, okay? Why would we need to split this problem into 2 different parts? Why do we have to do a level surface and an inclined surface? And focus on the work done by the force of gravity in your answer to this question. No. No. Focus about the work. Okay, so what can you tell me about when the box is moving just straight across right here? What is the work done by the force of gravity then? What's the formula for work? Are you asking me a question or telling me no?
It's force times the lever arms.
There's no lever arms in this.
Force times the displacement times the cosine.
Okay. Okay. So it is the force times displacement times cosine of theta. Now let's think about this block right here. Okay. So I've got this block. Which way is the force of gravity pointing? Down. Okay. Now which way is the block going to displace? Okay. It's going to go this way. What's the angle between down and to the right? Now, what's the cosine of 90? So are we going to have any work done by gravity in the first section? No. So if they're asking me, hey, what is the work done by gravity on the block, do we even need to concern ourselves with before it hits the ramp? No. Okay. That's why we need to actually split this up. Displacement is how far is it moving, okay, and in which direction. Okay. No, there is gravity, but the gravity's not doing any work on the box, okay? All right, so let's talk about the inclined surface then, okay? I'm going to move this up. We're going to work letter B first, okay? I feel like are y'all with me? Or are you like?
We're totally off today. We told you.
Wow. Okay, so well, we just said that this first section here is not going to have any work done by gravity. Does that mean that gravity doesn't exist in the first section? No, okay. So now we're going to try and figure out what the work done by gravity is in the second section. So again, what's the formula for work done by gravity? Okay, so the force is going to be the force of gravity times the displacement of the block times the cosine of theta, okay? Now, we can go ahead and expand this piece right here. Gravity has its own formula, right? What is that? Okay, times. Now, do you know how far up the ramp the block moved? Do we know what that displacement is? No. So that must mean, in order to answer this question, that piece of information is something we're going to have to try and find, okay? That's the thing that we're trying to figure out so that we can then go figure out what the work done by gravity is. Without that piece, we can't move on, all right? So I'm going to just leave that as displacement here. And now let's see if we can fill in the part about the cosine, okay? So we know it's going to be the cosine, but we need to know of what angle, okay? Okay, well, good question. What's the definition for angle in the work formula? Go back to your work formula and see what the definition of theta was. I want the definition first.
Is that right there?
I want the definition. Okay, we want the angle between the force vector and the displacement vector, right? So, which way is gravity going to be pulling? Down, okay? Oh, I really didn't mean to do that. Okay, so gravity's going to be pulling down, okay? And then which way is the displacement vector pointing? Okay, so the box is going up that way, right? Okay, so we need the angle between this movement and this movement, right? So if I do that, let's see here and here, okay? So I want this angle right here. Okay, now how am I going to do that?
180 minus 25. No, 90 minus 125 is some number, and you take 180 minus that number, and then you get that angle because that's they're supplementary. Or you can do that.
Okay, so if we look here in this bottom corner right there, okay, we know that this is what angle? 90, okay? So all we're trying to do is figure out what this little extra piece is, okay? And do you see that this triangle right here is a similar triangle to this one right here? Okay, so what is that angle going to be? 25. So what's the angle altogether going to be then? 115. Yes.
That's not mathematically right, but okay.
What?
So, like, where was the angle? Like, how do we know it's not that?
How do you know it was on what side?
On the side that we decided that
If you look at here, let me come over here. Okay, let me pull this forward. Okay, so we've already done this back when we did stuff on an inclined plane, right? Okay, if this is the displacement vector, let me move that down a little bit. Okay, so we know that this one was 25 degrees. We know that this right here is 90 degrees. So what does this piece right here have to be? 65 degrees. Very good. Okay, now if I come in here and put my X and Y axis on the center, okay, we know that this right here is 90 degrees, correct? So we're just trying to find this little piece right here. And if the whole thing, okay, if from here all the way over is 180, okay, then I've got the 65 piece of the puzzle right here, and I've got the 90 piece of the puzzle right there, and I'm missing this little center piece, and I know that all together they have to be 180, right? So how could I figure out what this little piece is right here? Okay, so I can say 65 plus 90, subtract that from 180, and I'll get this angle right here. So do that real quick and see what the angle is going to be.
25.
Very good. Okay, so this little piece right here, that's going to be your 25-degree angle. Okay, that's the one in between right here. Okay, this little piece, that's 25. That's the one I'm after, because that's the only one we didn't know. You need to know that angle so that you can come back over here to your picture and know that that angle is this one right here. We just applied the same exact process. We had this little piece right here is 90. I want to know what this piece right here is. If I know that that's 65, I'm trying to figure out what this is. Okay? All right. So we come up with our 115. Okay? Now, again, that's unknown still. That's the thing we're trying to figure out. And that displacement there is the displacement from the bottom of the ramp up to where the box stops, right? That's this, okay? All right. Any questions about that so far? No? Okay, cool. So let's go about plugging in our energy formula, okay? Conservation of energy is conserved when? There's only one situation in which energy is conserved. When is that? Yeah, when is that true? So when there's no friction present. Very good, okay? When there's no friction present, okay? So in order for us to do anything with energy, what do we have to do? Three things. You got to do three things. Three things have to be done to do an energy problem.
Zero line.
Okay, zero line. Where do you want the zero line to be? Okay. What else do you have to pick? And final point, okay? So we've got two separate situations, right? So let's say this is the initial point for situation number 1, and this is the final point for situation number 1. Where would the initial point for situation number 2 be? Good. And where's the final point going to be? Yeah, wherever the box stops. Okay, cool. Now, let's go through and write our conservation of energy formula. So we're going to put mechanical energy initial equals mechanical energy final. Because if you're looking at your...
You wouldn't be able to set those equal to each other on the thing.
Yeah, if we're trying to figure out what the displacement is up here, then we're going to need some more information, okay? All we have right now is an angle, okay? I mean, I need to know what a side and an angle is, and then I could find another side, right? And if I'm going to find the height, this vertical height, and I'm going to be using energy, which type of energy is going to have a height in it? Yeah, gravitational potential energy, okay? And if I've got gravitational potential energy and the box is moving, what other kind of energy does it have? Kinetic. What's the variables for kinetic energy? What's the formula?
1/2 mass times velocity squared.
Very good. So, and I know the mass of the box, right? So what do you think I'm going to need to know about the box? What else do I need to know about it? The velocity, right? So if I could calculate what the velocity of the box is just before it starts going up the ramp, then doesn't that mean that I know what the velocity of the box is when it starts moving up the ramp? Yeah, because those are two overlapping spots there. So I've got to figure out all this stuff in the first section so I can get that velocity so I can then plug it into the second section, okay? This is going to be a long problem, yeah. This is going to be fun. Okay, so
There's going to be one of these on the test.
here we go. Mechanical energy initial equals mechanical energy final. Now, look at the box in your picture on the left-hand side at the initial position and tell me, what kind of energy does it have at the initial position? Okay. Could have elastic potential energy, initial. Okay. Yeah. Now remember, you have to write everything and then we'll cross stuff out, right? So we've got elastic potential energy, which we know for sure it's going to have. We could have kinetic energy initial, and we could have gravitational potential energy initial, right? And what's that going to be equal to at the final point? And remember, the final point we're talking about is right before it goes up the ramp, okay? Okay, so yeah, kinetic energy final, gravitational potential energy final, and elastic potential energy final. Now, which kind does it actually have in the beginning? Okay. Oh, whoops. It's actually got elastic potential energy, so we're going to expand that. What's the formula for elastic potential energy? Fantastic. 1/2 times K times X squared, and this X is going to be X initial. What now? Oh, we're out of that. That's not this. X is the displacement, how much it compressed the spring away from the equilibrium position. Okay, good. So let's put our reasoning behind why we crossed this out. Is the box moving in the beginning? No. Okay, so we crossed kinetic energy out because the velocity was 0, right? Now, what's the formula for gravitational potential energy? Yeah, since it's on the 0 line, the height would be equal to 0. There is no height above the 0 line. So that's why those two canceled out. Okay? Now let's talk about the box right before it starts heading up the ramp. Okay? Is the box moving? Yeah, so we know for sure that there's going to be gravitational potential. Kinetic energy. So what's the formula for kinetic energy? Okay, 1/2 the mass times the, which kind of velocity? Final velocity squared. Okay. Does it have gravitational potential energy?
No, it's still on the 0 line.
Yeah, good. The height is still 0. It's on the 0 line. Does it have elastic potential energy? No, it did not run into a spring, so this is gone. Okay.
Wait, if both
No
people
spring.
bring 1/2, would that be half squared?
All right, so Garrett is right. Everybody brought 1/2 to the party, so we can get rid of the halves. Okay. All right. So now let's rewrite this. We've got the spring constant times the initial displacement of the box is equal to mass times the final velocity squared. Now, what is it that we decided we wanted to know here? Yeah, we wanted to know that final velocity, right? So what should I do? How? Okay, we'll divide both sides by mass, and then what? Take the square root of both sides. Okay, so my final velocity then is equal to the square root of the spring constant times x naught squared over mass. Yes, we do.
Yeah, we do. It's 2.0. Who gave it to us?
I have a question. Is it x squared type of equation or
No,
Now,
everything inside there.
the displacement of the box, it said it was compressing the spring by 35 centimeters, right? So if it's compressing the spring, it's moving away from the equilibrium position. In that picture, I had the equilibrium position where the spring would be if it was relaxed, but I've pushed in this way by 35 centimeters. So what number do you think I should actually plug in here since I was moving to the left? Yeah, negative 0.35 meters. Very good. Okay, so go through, type that in your calculator, please, and let's come up with an answer. And remember, when you introduce a radical, it's going to be plus or minus, right? And velocity is a vector, but we know which way the box is moving. Which way is it moving? It's moving to the right, so it's in the positive direction. Okay, so and do I want sig figs or do I want everything? I need everything. What's up?
So we're going to start the next second half. So is the final velocity for that one going to be 0 now?
Yeah, because the box comes to a stop. Yeah. All right, Isaac, what'd you get?
5.8562018.
Okay, focus over here. 1.8 what? All right, so that's the final velocity of the box in section 1, and it also happens to be the initial velocity of the box in section 2. Does that make sense to everybody? Okay, cool. Now, Shivam says that since the box is going to come to a stop somewhere up at the top of the incline, and we knew that because of one of the questions that they asked us. They asked us, what's the maximum height up the incline the box comes to? Well, if the box comes to a maximum height, then that means that it had to stop, right? In order to hit a maximum amount. Okay, so we know the final velocity of the box. We know the initial velocity of the box. What could we solve for here? Or what do we need in order to get that displacement? Remember, the whole point was we're trying to see the displacement up the ramp. What other piece of information could we get? Cool. How am I going to get acceleration of a box on an inclined plane?
Break it down.
FNet statements, forces. Very good. We're going back to forces, okay?
I'm still confused.
All right, so I'm going to split this into a little forces section real quick.
liked it better when we got stuck in kinetic equation. These new numbers really just don't make sense.
Like even when he gives us a start, I'm like,
We're going. We just went from the fourth increase all the way back to the second day in one problem.
I thought I was understanding it, but
we can never get a problem like this. I'm working on 4 pages of numbers.
All right, so if I did my free body diagram of that box on the incline, we know the incline has friction, and friction opposes motion, and we know that the box is going up the incline, so friction must be pointing down. We also know that there's going to be a force down the plane, which would normally cause any object on an incline to slide back.